Sound check one. Good morning. I'm going to give everybody another minute or two to log in. Okay, let's go ahead and get started. So today we're going to be talking about transformations of functions. And this past class that we had, we talked about a library of functions that we need to memorize, because we're going to take these functions and create new ones by adding numbers to them or multiplying them by a number or negating them. All kinds of different operations that result in things called transformations of the graphs. And the way that I would like you to go about it is to memorize these graphs and their key points. So we have the identity function, which is just the line y equals x. We won't be working with that one very much, but you need to know the name of it. Then there's the square function, f of x equals x squared. The square root function, f of x equals the square root of x. The absolute value function here, which is f of x equals the absolute value of x. The cube function, which is f of x equals x to the third power. The cube root function, f of x equals the cube root of x. And the reciprocal function, f of x equals 1 over x. So I'm going to go through each one of these one at a time and just remind you what the three key points or the key points and asymptotes are that you need to memorize for each graph. Okay, so let's start with x squared. It's always important on any type of shape of graph. This one's considered or called a parabola, but it's always important, no matter what it's shaped like, to label any points where the graph is turning around. So you can see here on this parabola, it has what we call a vertex at 0, 0, the lowest point, and that's where the graph turns around. So we're always going to want to label that. And then also the other 2 points I'd like you to label are negative 1, 1, and 1, 1. So those would be your three key points. And the purpose of these three key points is that if you can figure out where these 3 points move to when we perform an operation on the function, then you'll know exactly what the shape of the graph is. This is much more efficient than just trying to plot points where you don't know what part of the graph you're actually plotting. So, for example, a person might plot these 2 points up here and not know, just think they have a straight line when in fact they don't. So by being familiar with x squared, we'll be able to shift that around and get graphs like x squared plus 3, and we'll know where these 3 key points go. And I'll want to see those labeled on your paper when you take a test. All right, the square root function, we can only plug in positive values and 0. So you're going to see that all the x coordinates are 0 or greater. When you plug in 0 to the square root, you get 0. And this is an interesting graph because it actually has a terminating point. It doesn't go on forever in this direction. It ends right there. And that's kind of unique in these graphs. And then 1, 1 is another good one, because when you take the square root of 1, you get 1. I don't use 2 or 3 for my x values because then you get radicals. So I skip up to 4, 2. That's the next, 4 is the next perfect square. So that's an easy one to evaluate. So that'll be the third key point for the square root function. The absolute value function, which is interesting, it's the only one that comes to a sharp point. This absolute value function has actually the same 3 key points as the square function, 0, 0, 1, 1, and negative 1, 1. So the 3 points are the same, but the shape is different. So it's very important when you're graphing these that you get the shape, focus on getting the shape right. Most of them are very rounded, but not the absolute value function. It looks like a V. Okay, so let's go down here. This is the graph of the cube function. It goes through 0, 0, 1, 1, and negative 1, negative 1. Those are the 3 key points that I want you to plot every time you graph x cubed. You'll notice these 3 points actually lie on a straight line. So if you didn't know by memory that x cubed looks like half of a parabola going up and to the right and half of a parabola going down and to the left, if you didn't know that, you might draw a straight line, and that would be incorrect. The shape of these curves is very important. On the right, it looks like it's scooping upward like it could hold water, and on the left, it looks like it's scooping downward like water would pour out. And you should get that shape right when you draw it. Okay, a related graph related to x cubed is the cubed root of x. The inverse function, we call it. It reverses the operation of cubing. It actually goes through the same 3 points, but notice that the shape is different. Cube root and square root are going to be kind of on their side. They're going to look like a sideways version of the related x cubed and x squared functions. This one, again, is going to go up and to the right and down and to the left, scooping downward on the right and upward on the left. So get that shape right when you're drawing it. And by the way, the more practice you can get graphing on paper, the better. So if you're kind of bored sitting here listening to me, get out your paper and your pencil and start drawing, and that'll keep you busy and it'll help to reinforce the graphing skills. This is the reciprocal function. We talked about how it has a horizontal asymptote along the line y equals 0. The graph gets very close to that line in both the positive and negative directions, but never touches it because it's impossible to take the reciprocal of a number and get 0. And then it has a vertical asymptote at x equals 0 because 1 divided by 0 is undefined, so this graph doesn't actually cross the y-axis, x equals 0. So you need to memorize those two asymptotes and their equations, and then the key points for this graph are just going to be 1, 1, and -1, -1. And then you just follow along the asymptotes to get the graph. So I think I've covered all of these now. So this is the library of functions that you need to memorize and their key points. So now let's work with these. We're going to look at transformations of them. There are 3 types of transformations. There are translations, which are vertical and horizontal shifts. We talked about vertical and horizontal shifts in class yesterday, or sorry, the last time we met. We said that you'll get a vertical shift up or down by adding or subtracting to the function. We spent a lot of time talking about that if the change is on the outside of the function, it's going to affect the y coordinate. So this is a change in the y when you add a number or subtract a number to the whole function. This is outside the function, so it affects the y coordinate. And that's why you get a vertical change, because y values are up and down. To get a change in the x coordinate, we talked about if you have a horizontal shift, horizontal shift, it's going to come from adding or subtracting inside of the parentheses. An inside change affects the x coordinate. See how the add and subtract are indicated inside the parentheses? It'll be inside the parentheses, inside a square root, inside a cube root, inside the absolute value. When that change occurs, you know it's affecting the x coordinate. Now notice when you subtract from the x coordinate, you actually get a shift to the right, and when you add to the x coordinate, you get a shift to the left, which is the opposite of what you would expect. Generally, anything that happens inside the function, it does kind of the opposite of what you would expect, except for reflections. All right, So today we're going to talk more about reflections and stretching and compressing the graph. Reflections have to do with when you see a negative sign thrown in there. If it's a negative inside the parentheses, it negates the x coordinates, so it results in a horizontal reflection. If there's a negative outside the function, outside the parentheses, outside the square root, then it's going to affect the y. And then the same thing with stretch and compress. We have two possibilities, vertical and horizontal. You can stretch the graph away from the axis vertically and it gets taller, or we can compress it closer to it and it shrinks. And those are going to happen when we multiply a number outside of the function. And then whether it's a stretch or a compress just depends on if we're multiplying by a number bigger than 1 or a number smaller than 1. And then horizontal, it's a multiplier inside the function. And again, whether it compresses or stretches depends on the value of that number. All right, so what we're going to do is we're going to first look at reflections, and then we'll come back and look at stretching and compressing, and then we're going to look at what happens when you put all of the transformations together. All right, so I have here a few problems from my math lab, and remember, as I'm talking, you can ask questions. I see that Alan asked for the exam, do we need to memorize all of them? And the answer to that is yes. You need to memorize all of the graphs in the library of functions. In fact, for the next test, then we'll add to that library of functions. So it's important that you get these down now before we grow the library. Okay. Good question. Keep asking questions. Remember, there is a delay, first of all, between when I speak and when you hear me, and also it might take me a minute to see your message. So be patient. I will answer your questions. All right. So let's talk about this idea of reflections. Reflections have to do with when we negate a function. So the first thing I want to talk about is if you have a function f of x, and you know that the graph of that function goes through the point -7, -5. So you have the function y is equal to some equation f of x, and it goes through -7, -5. Then which of the following must be on the graph of y equals negative f of x? So this seems kind of abstract, but remember, all this is saying is that we're negating each y value. So when you have a negation on the outside of a function, not inside the parentheses, it affects the y coordinate, and it takes the opposite value of what it was before. So it doesn't affect the x-coordinate at all. The x-coordinate stays the same, but the y-coordinate becomes the opposite. So if you look down this list, which pair of coordinates has the same x-coordinate but the opposite y value? That's going to be this one here, -7, 5. Now it's going to do this for every single pair of coordinates on the graph. So let's think about what happens to a graph when we negate the entire function. In other words, negate every y value. So here it says use the graph of y equals f of x to graph the function g of x equals negative f of x. Now remember, f of x was just your y value. So what we're saying is g of x is going to be the opposite of every y value. So let's look at each one of these coordinates here and see what happens when we negate the y value. You don't have to look at every single coordinate. You can't, because there's an infinite number of them, but what you can do is look at key points, right? Now this is not one of our graphs from our library of functions. In fact, they don't tell us the equation of this function. but you can still identify key points where the graph ends, where it turns around, maybe its intercepts, any key points that help you to identify the shape of the graph. So for example, -4, 0, -2, -4, 0, 0, 2, 4, and 4, 0. These are important points on the to tell us about the shape of the curve of the graph. All right, now this is the graph in blue here of f. We're going to graph in red the graph of g. And the way we're going to do it is negate every y value. So for example here, -4, 0, that's going to stay the same because 0's opposite is still 0. But -2, -4, well, when we change the sign of the y value, that's going to become -2, 4. And then 0, 0 is going to stay the same because opposite of 0 is 0. And then instead of going through 2, 4, the opposite of 4 is going to be -4. So we're here at 2, -4. And then here we have 4, 0 stays the same. And so what happens is every single y value changes sign. Oops, I don't like how that looks. And so what was below the x-axis goes above, and what was above is going to go below. So we're going to get the same shape flipped over or reflected. Oops. One second here. Why is it doing that? Oops. It doesn't want to let me grab it. Okay. I guess I'll just freehand it. Let's see. All right, so connecting the dots. This is supposed to be straight. All right, we're gonna have a reflection over the x-axis. So you see how the left side flipped up and the right side flipped down. All right, so in general, let's look at this question. Select the correct choice. We're just going to fill in the blank. The graph of y equals -f of x is the graph of y equals f of x reflected about, and then you would say the x-axis. Why does it reflect across the x-axis? Because the x-axis separates all the positive y values from all the negative y values. So any y value that was up flips down, and any y value that was down flips up. So it reflects over the x-axis. Okay, that's when the negative is outside the function. All right, so now let's look at some specific functions from our library of functions and see what happens when we negate them. So for example, what if I asked you to graph g of x equals -square root of x using transformations? Okay, so when I ask you to do something like that, what I want you to do when I say use transformations is to use the reflection here of the parent function square root of x. So the first thing you have to do is to identify your parent function. Right, so you have memorized this parent function. Oops. And so let's draw a picture of it and its key points. Okay, so what would be the parent function for negative square root of x? Well, since it has a square root, we're talking about the function f of x equals square root of x. F of x equals square root of x, remember, is a half of a parabola going to the right. F of x equals square root of x. I'm going to graph in gray. It has a terminating point at 0, 0, goes through the point 1, 1, goes through the point 4, 2. So this is what the graph of square root of x looks like. But we want negative square root of x. The negative is on the outside, so it's affecting the y coordinate. So what that means is every key point, we're going to change the sign of the y coordinate. So 0, 0 is going to still go through 0, 0 because the opposite of 0 is still 0. But 1, 1 is going to flip over the x-axis and go to 1, negative 1. And 4, 2 is going to flip over the x-axis and go to 4, negative 2. Like this. So it's a reflection across the x-axis. Now, something that helps a lot of students is to actually write the key points from the original function off to the side, and then think about what's happening to each pair of coordinates. So we're going to negate each y value. So that's why we get 0, 0, we get 1, negative 1, and we get 4, negative 2. So for a lot of my students, they like to actually write this little chart out and then go through and plot those points and draw in the shape. But it's also okay if you recognize that this is going to be a vertical reflection, okay, which you should associate a negative outside the function with a vertical reflection to just start drawing it directly onto the graph, whatever works for you. Okay, now what would happen if that negative were inside of the radical? We actually graphed this one in class last time, or one like the following problem. What if we had, for example, to graph f of x equals, oh, I don't want the gray right now. Okay, so we're going to graph f of x equals the square root of negative x. All right, so in this case, is the change to the function, is it inside or outside the function? So what I mean by that is it inside or outside the radical? The negative in this case is inside the radical. And so it's inside the function. It affects the x coordinate. Okay, so in other words, instead of changing every x coordinate, every y coordinate from positive to negative and vice versa, we're going to do that to the x coordinates. So we're going to go ahead and first identify our parent function. Let me write that down. We're going to first identify the parent function, which all that means is look at the function and see what it's a variation on. This is a variation on y equals the square root of x. Second, we're going to graph the parent function and label its key points. Okay, so in this case, once again, we have the parent function that looks like half of a parabola going to the right. So we're going to graph plot 0, 0, 1, 1, and 4, 2, and graph that parent function. Make sure that this does not look like a straight line. It should have some curve to it. All right, especially for those of you who are going to go the calculus route, you definitely need to be graphing the shapes accurately. We're going to be very concerned with the shapes of functions once we get into calculus, so you need to make sure it has that little curve to it. All right, and then we're going to, so this is the graph of y equals the square root of x, but we want f of x equals the square root of negative x. And so we know that we're going to take each one of the key points and we're going to negate its x coordinate. Okay, the change that's occurring here is to change every x to a negative x. So the opposite of 0 is still 0, so that stays the same. The opposite of 1 is negative 1. The opposite of 4 is negative 4. So we're going to plot 0, 0. We're going to plot negative 1, 1. And we're going to plot negative 4, 2. And so what's happening here is every single point along this whole curve is flipping over the y-axis this time. So we're going to get a reflection over the y-axis. It looks like a mirror image, but going to the left. Okay, so in general, the graph of y equals f of negative x is the graph of y equals f of x reflected over the y-axis. And this is called a horizontal reflection. So yes, to answer your question, this is the horizontal reflection. Okay, that's when the negation is inside the function. All right, so going back to our list of transformations then. All right, the first day of class we did vertical shift and horizontal shift. Now we've done vertical and horizontal reflections. And then the next topic is going to be stretching and compressing. We're going to have a vertical stretch and a vertical compress, and then we'll have horizontal stretch and compress as well. So let's take a look at that. Okay, so here's an example from my math lab. It says graph the function using the techniques of shifting, compressing, stretching, and or reflecting. Start with the graph of the basic function shown below. So in the graph that they want us to graph is g of x equals 7 times the square root of x. Now they're telling us the parent function. You don't have to identify it in this case. This is given to us. That will not always be the case, but it is in this case. So here's the graph of y equals the square root of x. Notice it goes through the key points that we've discussed. It goes through 0, 0. It goes through the point 1, 1. And it goes through the point 4, 2. Okay? What I recommend is when you're working this problem at home, it's a multiple choice question, and you might be able to just look at it and identify which one is correct. But on your test, you will have to graph a couple of these on paper, so you need as much paper practice as possible. So instead of going directly to the answer and picking one, I would recommend that you go ahead and graph the parent function and then graph, plot the key points and graph the new function. All right, so anyway, let's look at this. Let's analyze what's happening here. We have taken the number 7 and we're multiplying it times the square root of x. The original function, every y value was just the square root of x. But now every y value is going to be 7 times that amount. So again, whenever you have an operation going on outside of the original function, outside of the parent function, it's going to affect the y value. So in this case, instead of going through the point 0, 0, we're going to figure out what point this new graph is going to go through by taking 7 times the y coordinate. Same thing with 1, 1, same thing with 4, 2. 7 times the y coordinate. So we're going to have points, 7 times 0 is still 0, so that stays the same. 1 times 0 is, 1 times 7 is 7, so goes through 1, 7. And then for 4, 2, we have to multiply the 2 times 7, so that's going to be 4, 14. Okay, so on our graph, we're going to plot 0, 0. And then we're going to go through 1, 7. Make sure you're labeling these because when you do it on your test, I want them labeled. And then 4, 14. And so we have a graph. Whoops. Graphs never go backwards like that. Let's see. So we have a graph. It's hard for me to draw because it's really stretched out. But it looks something like this. Okay, so then once you've graphed it, see how it's stretched away from the x-axis? Stretching upwards away from the x-axis. It's a vertical stretch. All right, so we would select our answer over here and it would be B. Okay, but graph it on paper first before you look at the multiple choice options. All right, let me erase this. There we go. Okay, so the reason why it grew so much is because we were multiplying y by a big number, 7. Now, if you multiply y by the number 1, nothing will happen, right? If you multiply by a number bigger than 1, like 7, it stretches like this. And what do you think would happen if you multiplied by a number less than 1, like a half? So if we multiplied each of these y values by a half, half of 0 is still 0, half of 1 would be a half, and half of 2 would be 1, and the graph would actually shrink closer to the x-axis. So whether it stretches or shrinks is really just a matter of whether the multiplier is bigger than 1 or less than 1. So let's write that down. Okay, so the graph of y equals a number a times f of x is the graph of y equals f of x, and then it's going to be stretched vertically if a is greater than 1, and it's going to be compressed vertically if a is between 0 and 1. I don't just say less than 1 here because I don't want negatives. If there's a negative, that's a different thing. That's a reflection, right? We already talked about that. Okay, so let's look at this one. Here we have the graph. We're asked to graph using transformations the function h of x equals 1 over 8x. They also ask us to find the domain and range of the function. All right, so let's look back at our library of functions and see what the parent function might have been. We need to identify our parent function. So going back over here, remember the function we're working with is 1 over 8x. So that's closest to the reciprocal function 1 over x. So that's going to be our parent function. Now 1 over 8x could be thought of as h of x equals 1/8 times 1 over x. So there you can see where the 1 over x is in our function. So the parent function would be f of x equals 1 over x. Okay, so we've identified our parent function, and we're going to graph it, and then we're going to think about how it's going to be transformed. So I'm going to put in a graph here. Okay, so if you recall that this is called the reciprocal function 1 over x, it's the special one that has two asymptotes. So always draw your asymptotes first, because that will help guide you in drawing the rest of the graph. So first asymptote is on the y-axis. Do you remember the equation of this line? A lot of times people think it's y equals 0 because it's the y-axis, but that's not true. Every point along this line has an x-coordinate of 0. So this is x equals 0. And then along the x-axis, every point has a y-coordinate of 0. So this is y equals 0. So don't get those two mixed up. And then the key points that we graphed were 1, 1, and -1, -1. And remember, it follows along these asymptotes. Looks like this. This graph is actually called a hyperbola. If you take pre-calculus, you'll learn about graphing hyperbolas. Oops. Okay. So here's the graph of our parent function. Now, how is this function, which I'm going to label f of x equals 1 over x, how is this different from h of x equals 1/8 times 1 over x? So the 1/8 being out front here tells us that we have a vertical change because it's outside the fraction, outside the function. I'll show you in a minute how you can think of it as being inside as well, and it'll still work out the same. But right now we're going to think of it as being outside the function, and it's being multiplied by a number that's between 0 and 1, a fraction. So what that means is that we're going to get a compression outside the function affects the y, and so it's a vertical compression. Vertical compression. All you have to do, though, is take each of the key points and asymptotes and multiply the y values by 1/8. So we have y equals 0, x equals 0, we have 1, 1, and we have -1, -1. And we're going to change these points by multiplying any y values by 1/8. 1/8 of the y value. Well, if y is 0, 1/8 of 0 is still 0. So that's going to stay the same. Okay, so we're going to have y equals 0 is still an asymptote. X equals 0 doesn't change because only y values are affected. 1, 1 is going to change to 1, 1/8 because 1/8 times 1 is 1/8. And -1, -1 is going to be -1, -1/8, multiplying that y value by 1/8. All right, so the asymptotes didn't change. There's still going to be these green asymptotes. But the key points did. 1 1/8 is the first one here. And the graph is still just going to follow along here. It's just a little squished a little closer to the x-axis. And then -1, -1/8 also squished a little bit closer to the x-axis. Okay, so in my math lab, if you had to select the appropriate graph, I wonder how hard it is. Oh, I didn't copy it big enough. Definitely D is out. Definitely. Oh, yeah, it can't be this one or this one because they're both on the same side of the axis. The reciprocal function, you have half on each side. So it's got to be C here. But again, on the test, some of the questions might be multiple choice where you can use process of elimination, but there will definitely be at least a couple where you have to graph it on paper. So practice that as well. All right. Now let's see what happens when the change occurs inside the parentheses, inside the function. So here is an example where we have g of x equals f of 2x. They're giving us the graph of f of x, not the equation of it. Okay, but what this is saying is that the y value that you get for g when you plug in x is going to be the same y value that you would have gotten if you plugged in double x to f. So you kind of have to work backwards and think, okay, so I'm going to have to half the x values. Anytime you have something, an operation happening inside the function, it's going to affect the x values, but usually in the opposite way that you would think. So if we have 2 times x, then in this case it would be 2 divided by x. I'm sorry, not 2 divided, x divided by 2. X divided by 2. Half, in other words, of x. Okay, so it's kind of weird, I know, but that's the effect it's going to have on any key points. The key points that we're looking at are, let's see, -6, 0, -4, 1, 0, 0, 4, 1, and 6, 0. So let's go ahead and take half of each x coordinate and keep the y coordinates the same. So we're going to have -6, 0, I'm sorry, not -6, 0. Half of -6 is -3, 0. Half of -4 is -2, 0. Half of 0 is still 0. Half of 4 is 2. And half of 6 is 3. So we're going to graph -3, 0, which would be here. We're going to graph that should have been a -2, 1, excuse me. -2, 1, which is here. We're going to keep 0, 0. And we're going to graph 2, 1. And we're going to graph 3, 0, that should have been. Whew, I got to be careful. The y values stay the same, 3, 0. So it's going to have the same, oop, something's not right. -3, 0. That should have been a -4, -1, so that should have stayed down low. Sorry about that, guys. -2, -1. The reason why I caught my error is because it should be the same shape, just squished closer to the y-axis. Okay, so it looks like this. So you see how it was squished closer inward towards the y-axis? because each x value was halved. Okay. All right, so that's what happens when you multiply inside the parentheses, inside the function, where the multiplier 2 is greater than 1. It actually squishes it closer, the opposite of what you would think, closer to the y-axis. So this is called a horizontal compression. Now, if we had multiplied x by, say, 1/2 in there, then we would have done the opposite of taking half of x. We would have doubled it, and we would have gotten a graph that was stretched further away from the y-axis. Oops, I got that one in there twice. Let's see here. All right, so we're not going to graph this one, but you tell me, what type of transformation would this one be? So we have h of x equals 7x cubed, and the parent function is f of x equals x cubed. Which of these options describes the transformation that has to occur to get the right graph? So again, we're looking for h of x equals 7x cubed. So what you want to be thinking about is this 7, what's the operation that's happening with the 7? It's multiply. Is it being multiplied on the inside of the function or the outside of the function? Because that's going to tell you whether it's affecting the x or the y. Multiplying tells you if it's a shift, a stretch, or a reflect. Inside or outside tells you, is it horizontal or vertical? So what do we have here? Anyone want to be brave and type it into the chat bar for me? What do you think? A, B, C, D, E, F, G, H, I, or J? Not sure? Okay, so let's go back to our list of the different types of transformations, right? So, I'll clean this up a little bit. All right, so let's look at the different types of operations and what type of transformations they are. So for example here, this is when we add a number to the outside of the function or subtract a number to the outside of the function, you get a vertical shift. When you add or subtract a number inside the function, you get a horizontal shift. If you put a negation outside the function, you get a vertical reflection. If you put a negation inside the function, you get a horizontal reflection. If you multiply by a number on the outside of the function, then you're going to get a vertical stretch or compress depending on the size of the number, if the number is bigger than 1 or less than 1. And if you multiply a number on the inside of the function, you're going to get a horizontal stretch or compress depending on the value of the number. All right, so what we were looking at was h of x equals, h of x equals 7x cubed. All right, so which one of these does it fit? the original function x cubed is here. We have multiplying that function by a number 7. It's on the outside and it's being multiplied. So it's not being added, it's not being subtracted. It's definitely not on the inside of the function. It's not negating, so it's not either of these. Okay, it's on the outside, not the inside, so it's not a horizontal stretch or compress. It's a vertical stretch or compress. And which one is it? Stretching away or compressing toward the axis? Well, since a is bigger than 1, we have this case where we're stretching away from the x-axis. Right? When you multiply every y value in the original parent function by 7, you're making it bigger. So here we go. Let's see. We're not shifting. We're stretching the graph, but is it horizontal or vertical? Because it's affecting the y value, because it's on the outside of the function, it's going to be a vertical. So this would be a stretch vertically by a factor of 7. Okay. All right. So now we're going to see what happens when, well, let's since there's some confusion about some of these things, let's go ahead and look at a few more examples where we identify what type of transformation we have. All right, so I'm going to just jot down a few functions like, let's do y equals cubed root of x plus 2, y equals negative cubed root of x, y equals 1/3 cubed root of x, and y equals the cubed root of 2x. Oops. Yeah, that's right. Okay, so we have 4 different functions. They're all based on the parent function, the cubed root of x, but I'm not going to graph it. I'm just going to identify what type of transformation we have. Okay, so when you're adding or subtracting to the, well, first of all, hello, Talon. When you're looking at these functions, first identify whether the operation is affecting the inside or the outside of the function. So for example, this one, the operation is on the outside. It's not inside the root. Also, this one is on the outside. Also, this one is on the outside. But this one is on the inside. So what that means is that these first 3 affect the y coordinate, y coordinate, y coordinate. But this one affects the x coordinate. Oops. Okay, so what that means is when we're identifying the transformations, anything that affects the y coordinate that's on the outside, that's going to be a vertical change of some kind. So each one of these is going to be some kind of vertical change. But this one is going to be a horizontal change. Okay. Then you look at the operation, plus 2. If you're adding 2 to every y coordinate, what kind of vertical change is it going to be? It's going to be a vertical shift upward by 2 units. Okay, now on the other hand, if we negate on the outside, we're negating every y value. So every one that was positive becomes negative and vice versa. We're going to have a reflection. And is it going to be a reflection over the x-axis or the y-axis? Well, it's the y coordinates that are changing, right? From bottom to top or top to bottom. So you're reflecting over the x-axis. All right, now how about this one? 1/3 cube root of x. We know it's a vertical change that's being multiplied. So that's either a stretch or a compress because you're multiplying every x value by a factor. Now, if you multiply every x by 1/3, it makes each x value smaller. So this is going to be a vertical, I'm sorry, each y value. It's going to be a vertical compression. We're multiplying each y value by a third, so it makes each of them smaller. So vertically it shrinks it or compresses it closer to the x-axis. And then lastly, y equals the cubed root of 2x. We're multiplying. We already decided it's a horizontal change because the number's inside the root. But we're multiplying x by 2, which means, remember, when we do things inside the function, it has the opposite effect. So multiplying by 2 really divides each x-coordinate by 2, or takes 1/2 of each x-coordinate. So what that is a horizontal compression. It would have been a horizontal stretch if it had been a fraction. Let me show you what an example of a horizontal stretch would look like. Y equals the cube root of x over 3, for example, is still inside the function. It's still affecting the x-coordinate, but you can think of this as 1/3 of x. This number is between 0 and 1. It's a small number. It shrinks the x value. I'm sorry, I just said that the wrong way. It's a small number. You would think it would shrink the x value, but since it's inside the function, it does exactly the opposite of what you would think. Inside does the opposite. So you're actually going to take and multiply each x value by 3. So that's going to be a horizontal stretch. Okay. All right, so a 1/3 on the outside causes a vertical compression. A 1/3 on the inside causes a horizontal stretch. It does the opposite of what you would think. All right. So now we're going to look at the order of transformations, meaning when you have multiple transformations inside of the same function, how do you deal with that? So different books do this in different ways. Our textbook uses the following order of transformations. It's okay that different books do it different ways because there are different options for how to go about it. But whatever way you pick, stick with it, because if you do it wrong, if you do it in an order that doesn't work, you're going to get a graph that's incorrect. So the order does matter. So the way that our book does it is, it says first you do any horizontal shifting. Okay, so a horizontal shift would be something like maybe adding 2 inside of the square root. Anytime you add or subtract inside of the function, you get a horizontal shift. So this is an example of a horizontal shift. Then you're going to do any stretching or shrinking. As we just discussed, anything you multiply times the inside or outside of the function. So for example, y equals 2 times the square root of x, or y equals the square root of x over 2. These are both examples of stretching and shrinking, just in different directions. And then you're going to do any reflections. Remember, reflections are just where you have a negative on the outside or a negative on the inside of the function. And then we're going to do any vertical shifting last. Vertical shifting happens when you add or subtract outside the function. Okay, so let's look at, so this is an order that you need to memorize. Horizontal shifts, then stretching and reflecting, and shrinking, then reflecting, and then vertical shifting. So here's an example. Let me make it a little bit bigger here. Okay, so here's an example. It says, begin by graphing the square root function f of x equals square root of x, then use transformations of this graph. Okay, so if we are looking at g of x equals 1/4 square root of x plus 5. There are two operations being done here that weren't done in the original square root of x function. There's being multiplied by 1/4, and then there's being the 5 being added. All right, so the first thing you need to do is to identify what types of transformations these are. So in my math lab, it's going to give you a list, and you just select any and all from the list. So what is the 1/4 doing? So when you decide that, you got to think about, first of all, the fact that it's on the outside of the function means it's affecting the y value. So it's got something to do with vertical. Y is always vertical. So what's happening? Well, then you think about its multiplication. Multiplication, multiplying and dividing, have to do with stretch or compress. Okay, so we have, it's either going to be a vertical stretch or a vertical compress. The number 1/4 is between 0 and 1 though. So since we're outside the function, and when you're outside the function it does what you'd expect, taking 1/4 of each y value is going to give you something smaller. So it's going to be a vertical compress. So we need to find where we have shrink and compress. By the way, I use these words interchangeably. So it's a vertical shrink if you want to think of it that way. So this first one says shrink the graph vertically by a factor of 1/4. And so that would make sense. So that's one of the two transformations. Now, what does it mean when you are adding 5 inside of the function? Okay, so adding 5 inside the function, first of all, since it's inside the function, under the square root, you want to think, is it affecting the x-coordinate or the y-coordinate? Well, it's being added to the x, so it's affecting the x-coordinate. It's inside, it affects the x. And since it's inside, it does the opposite of what you would think, right? So what's actually going to happen is you're going to subtract 5 from each x-coordinate. What effect does that have on the graph? Well, when you have addition or subtraction, that's always a shift. We're affecting the x-coordinate, so it's a horizontal shift. And it's going to be to the left because you're going to subtract 5 from each x-coordinate, do the opposite of what you would think, you go to the left, 5 units. So the next answer, shift the graph 5 units to the left, would also be correct. All right, so in which order should we do these things? So let's go back up here. Since we have a vertical shrink, any stretching or shrinking is the number 2 step. And a horizontal shift would be the number 1 step. So what we're going to do is we're going to shift horizontally, and then we're going to stretch or shrink. Now, one way you can do this, instead of having to graph multiple graphs, is you can start with your key points from your original function and move them in, perform the operations on them in that order. So here's what I mean. Remember, our square root function goes through the point 0, 0, it goes through the point 1, 1, and it goes through the point 4, 2. It looks like half of a parabola going up and to the right. So I'm going to write down my 3 key points, 0, 0, 1, 1, and 4, 2. And I'm going to think about 2 changes. The first change is going to be the horizontal shift. I'm going to subtract 5 from x. Remember, since it's inside the inside operations do the opposite of what you think. So instead of adding 5, we subtract. So subtracting 5 from each x would give us negative 5, 0, negative 4, 0, and negative 1, 0. But that's not the only change we need to do. We also need to multiply by 1/4 each one of the y values. So 1/4 times the y is going to give, oh, I did it again. What is it with me writing zeros here? That's funny. Okay, those y values stay the same. So it should have been negative 4, 1 and negative 1, 2. There we go. All right, now we're going to multiply each of these by 1/4. So that's going to give us negative 5, 0. 1/4 of 0 is still 0. So still negative 5, 0. And then we're going to look at negative 4, 1 becomes negative 4. 1/4 times 1 is just 1/4. And then negative 1, 2. 1/4 of 2 is going to be 2/4 or 1/2. So negative 1, 1/2. Okay. Oh, this is going to look really tiny. I'm going to change my original parent graph. I'm going to make it a little bigger so we can all see it a little bit better. Come on, there we go. Okay. So for my original parent function, which I'm going to graph in red, let's do a scale of, let's make this 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. I need to go out to negative 5. Okay. All right. I think that should do it. Okay. So our original parent function was a square root function. It goes through 0, 0, goes through 1, 1, and it goes through 4, 2. And it looks like this. Okay. Our first step, well, you can either graph each step to help you kind of see where the shape is going, or you can jump to the end. I'm going to graph each step just this time so you can see what happens. So first we shifted to the left 5 units. So it goes through negative 5, 0, goes through negative 4, 1, and it goes through negative 1, 2. Okay, so it's the same shape, just shifted to the left 5 units. All right, but then we had to compress it vertically. So it still goes through negative 5, 0, but it also goes through negative 4, 1/4, which would be about here. And it goes through negative 1, 1/2. So the final graph looks like this. Okay, it's the same shape, but shifted to the left and compressed closer to the x-axis. All right, I want to do one more before we sign out, so let's try another one. Okay, this one, instead of being one of our library of functions where we graph the parent function, they're giving us a random function. They don't tell us the equation. This blue graph is supposed to be the function f of x, and they want us to graph. Let me zoom in a little bit here. Okay, they want us to graph g of x equals 2 times f of x plus 4 plus 1. So we actually have 3 different operations going on here. We have adding 4 inside the parentheses. We have adding 1 outside the parentheses. And we have multiplying by 2 outside the parentheses. So we need to identify what each of these transformations is, and then we need to refer to our order of transformations to decide what we're going to do first and second and third. So this 2 here is multiplying, so it's a stretch or compress. It's on the outside of the function, which means it affects the y coordinate, and since it's bigger than 1 and it's outside, it's going to be a vertical stretch. You're going to actually multiply every y value by 2. And then this plus 4 here, that's inside the function, so it's a horizontal, it's affecting the x coordinate. You do the opposite of what you would think, so it's going to be a horizontal shift to the left 4 units. You're actually going to subtract 4 from each x. And then this other one over here, plus 1, is on the outside of the function, so it's affecting the y coordinate. It's addition, so it's a shift, and it's going to be in the positive direction up. So this is going to be a vertical shift. A vertical shift upwards 1 unit. You're going to actually add 1 to each y coordinate. Okay, so now let's look back at the order in which we would do a vertical stretch, a horizontal shift, and a vertical shift. So we do any horizontal shifting first, then any stretching or shrinking, then any reflecting, but we don't have one of those, and then a vertical shift is saved for last. Okay, so horizontal shift, then stretch, then vertical shift. So we're going to do horizontal shift, then the stretch, and then the vertical shift. First, second, third. Okay. All right, so let's start by identifying our key points here. All right, so we have -4, 0, -2, -2, 0, 0, 2, 2, and 4, 0. And we're going to do step 1. We're going to take each of those points and shift it horizontally by subtracting 4 from the x. So writing down my key points, -4, 0, -2, -2, 0, 0, 2, 2, and 4, 0. Let's see where they're going to go. All right, so we're subtracting 4 from each x. So we're going to have -8, 0. We're going to have -6, -2. We're going to have -4, 0. -2, 2, and we're going to have 0, 0. All right, and then after that, that's the horizontal shift to the left. Then we're going to stretch it by a factor of 2, multiplying each y value by 2. So the next thing we're going to do is 2 times each y coordinate. Okay, so that's going to be -8, 0, -6, -4, -4, 0, -2, 4, and 0, 0. And then the last thing we're going to do is we're going to do a vertical shift up 1 unit, adding 1 to every y. So we're going to take every y value and we're going to add 1 to it. Okay, so -8, 1, -6, -3, -4, 1, -2, 5, and 0, 1. All right, so let's plot these points. We have negative 8, 1. We have negative 6, negative 3. We have negative 4, negative 1, or sorry, negative 4, positive 1. We have negative 2, 5. And we have 0, 1. So now we're going to connect it, and it should look like the same basic shape, but again, we've shifted it to the left, we've stretched it away from the axis, and we've vertically shifted it up a unit. And please label each of your key points so I know what you've done. Okay, so that red graph would be the graph of g of x. All right, I hope you found the live chat helpful. If you did, please give it a thumbs up to help other students find the video. If you have any follow-up questions, feel free to contact me by Skype or email. I prefer not to use the D2L email, so any of the other emails that I gave you in your syllabus would be fine. All right. Thank you for logging in today. Have a great weekend. And by the way, I'm about to log back in for another live chat. So if you get a message, that's what's happening. It's for a different class though. All right. Have a good weekend.